Biomembranes are dynamic structures with unique characteristics that determine its specific functionality. As in so many other biological systems, the lipids, proteins, and sterols of the membrane are subject to the fundamental principles of thermodynamics, including entropy and enthalpy. Commonly explained using an XY plot with a generic reaction coordinate on the x-axis and Gibbs free energy on the y-axis, a reaction will proceed spontaneously in the forward direction if its activation energy can be overcome and the change in delta G is negative or exergonic. Just like a boulder rolling down a hill, the reaction will easily proceed once it is thermodynamically favorable. In the case of the membrane, its components must be arranged in a specific way to minimize energetic costs. The extensive hydrogen bonding between water molecules helps explain the hydrophobic effect seen at the membrane. The aggregation of water molecules around a single fatty acid chain causes a decrease in entropy, and thus lipids are aggregated with nonpolar regions packed closely to avoid unnecessary contacts with aqueous layers. Hence, we see layers of polar or nonpolar motifs clustered together and not always in a laminar fashion. These aggregations can be cylindrical, spherical, and even invert their nonpolar regions externally if dissolved in nonpolar solvents. In the typical biomembrane, we see a laminar arrangement of phospholipids into a nonpolar core and polar exterior with various proteins and sterols stuck into the membrane. The special characteristic of these components is their amphiphilicity, or that each component has both a polar and a nonpolar region. This duality relies on the hydrophobic amino acids inside proteins and the hydrocarbon chains of the acyl groups, as well as the hydrophilic residues of external proteins regions in the charged phosphate heads of the phospholipids. This allows small nonpolar molecules and a few water molecules to easily slip through the bulk of the lipid bilayer, whereas larger polar molecules must enter via protein channels or cellular transport mechanisms like endocytosis. This selective permeability is what allows the cell to maintain various gradients and compartments in order to keep a relative state of equilibrium. One of the most exciting features of the biomembrane is the relative mobility of its constituents. Individual phospholipids are capable of moving in several ways. 1. Rotational movement, or spinning in place, which is largely affected by acyl chain length and saturation. 2. Transversely, hopping across the leaf of the membrane. 3. A swinging motion, again largely determined by acyl chain qualities. 4. Transversal diffusion, which occurs at low rates but is facilitated by enzymes including flippase, floppase, and even scramblase.